Yes. No, that's what Svetlana is going to solve before the end of the conference. No, so those of you who are experts in landscape will not learn anything from this talk. So by all means, do your Facebooking or what others. But I presume there are still people here who are not experts. I was not an expert, and I learned. I didn't become an expert, but I learned the things, and I kind of, this was fun. And let me tell you a little bit about this. So I spend lots of time on Math Overflow, which is this site where professional mathematicians ask questions. I'm not a professional mathematician, but I enjoy their company. And occasionally there are physics questions. And once or twice I get good physics ideas there. And this was actually a post by Viktor Galitsky, who was supposed to be here. Unfortunately, he's not here. And he asked these mathematicians, what is this crazy? There's this crazy paper, talk by Mayborda, where you can diagonalize some Hamiltonian without solving actually an eigenvalue problem, just by solving a partial differential equation. This is crazy. What do you think? That was Victor's talk, and somehow I was intrigued by this, because this is what I do for a living, right? Solve eigenvalue problems. So I thought I had to learn about this. I even wrote a little commentary on that. And then I thought, okay, but let's see if I can do some original, some research of my own on this, because this is really intriguing. And I work on topological states of matter, graphene. So there the fundamental wave equation is the Dirac equation. All the work of Mayborda and Philoche was obviously a Schrödinger equation. And so the obvious thing to do is say, can we extend this from the Schrödinger equation to the Dirac equation? And the answer is yes, we can. And that's what I'll be telling you in the next half hour or so. And by all means, again, just interrupt me. The talk is not long, and I'll end before coffee. So interrupt me, ask questions, and it will make it more lively. So yes, I'm slightly embarrassed here with the two founding father and mother sitting here, but I'll walk you through the way I discovered this and understood this, and it's never bad, I think, to hear it's summarized from a perhaps slightly different perspective. So this is the famous paper, right? 2012, 10 years ago already. Kind of crazy weak localization. In my field, we know very well what weak localization is, but that's not what you guys think it is. So here it's meant, weak localization here is meant localization by not very high potentials. We in physics, we have a different word for that, but so yes, these are the figures, I think, which Svetlana showed already day before yesterday. Landscape function which closely maps the peaks of the localized states. Landscape function is some magic function, and it has peaks where the wave functions localize. So that's interesting, because you might want to know where they're localized for even for technological reasons. And I'm going to walk you through two slides which just summarizes the Mayborda-Philoche inequality, because I need that, because then my question is, how do I generalize this to the Schrödinger equation? So the landscape function is some function, u of r, which is an upper bound on an eigenstate, and the upper bound has this form here. So you see, this is the eigenstate. It's normalized by maximum. So on the peak of the eigenstate, the left-hand side is 1. If the eigenstate peaks, the left-hand side is 1. Here's this function u, and then there's energy. So if the energy is small, the left-hand side becomes 1, the energy is small, so this u better have a peak there. Otherwise, the inequality will not work. In fact, so this function u is where this function is bigger than 1 over e. That's where the wave function will peak. So that's why it's called. That's the landscape function. That's useful. And then comes the discovery. The discovery is that if you have the Schrödinger operator, here it is, minus Laplacian plus some disorder potential. Disorder potential has to be positive. You'll add some constant if it's not. Then you find u by solving a partial differential equation. Here it is. So this is one. It means it's a field which is 1 everywhere, and u is some other field, and it solves this equation. And solving one PDE may be expensive, but you get lots of information at different energies, which otherwise you would be much more expensive. So somehow this is certainly computationally efficient. Then, of course, there's much more work, which I'm not going into. This U has a life of its own. It's not just a computationally efficient way to find localized eigenstates, but it's some sort of smooth potential. And we've heard Svetlana talk about that day before yesterday. But my perspective here is very limited. I just say, okay, this is a convenient way to find out where states localize. I want to do that for graphene, for example, the Dirac equation. So I need to show you one more slide, which is basically this inequality here. I want to derive this inequality for you, because I want. Okay, I probably this annoys Michel, so I'm probably going to skip that. So here's the proof. So it's just a few lines of so this is the absolute value of psi. Psi is an eigenstate, right? So if this is the inverse of the operator, then this gives you 1 over E, and then I multiply by E, so this is just an identity. First thing is done, good. Then there's this thing which I think is Cauchy-Schwarz, where the absolute value of this product is always smaller than the product of the absolute values. Okay, good, that's another good thing. Then, okay, I do something very silly. I say psi is at most equal to psi max, so I'm just going to replace psi by psi max. I'm going to replace it by 1 times psi max. Then I can take psi max out. Where did it go? Okay, again, lost my... So this Newton's equation integrator sometimes fails. That's unfortunate. But anyway, I take psi max out. Now it's here. There's 1 here. And now comes the key step. All of this is kind of very silly and simple. Now comes the key step. And the key step is that you remove the absolute value signs here. Why can you remove the absolute value signs? Because this inverse is positive. Now this is something crazy, So this inverse, you'll recognize it. It's the resolvent or the Green's function of the Schrödinger equation. I work with resolvents every day. I have lots of colleagues who work with Green's functions every day. We all know that the Green's function is positive definite. I mean, this is like kinetic energy plus potential energy. If potential is positive, it's positive definite. Of course, if a operator is positive definite, its inverse is also positive definite, right? But that's not what's meant here. So this greater equal sign here is something which is kind of unusual. I've never encountered this before. It means pointwise positive. Typically, if you ask, is a matrix positive in linear algebra, we mean, does it have positive eigenvalues? That's not what's meant here. This inequality sign means pointwise positive. So think of this like a big matrix. R and R prime are like indices, rows and columns. Every single entry of the matrix is positive. That's of course a very different notion than positive definite. And I even ask around to learned colleagues, did you know that the inverse of the Green's function is pointwise positive? I mean, physicists if you Google it, you'll find that it's true, but physicists are unaware of very, very basic things because we never bother with pointwise things. So anyway, because it's pointwise positive, this is true. It's because it's a property of a maximum principle for elliptic operators. That's why it's positive. Yeah, but okay. I asked Piet Brouwer, who's a high-level professor in Berlin, did you know that the inverse of the Green's function is positive, pointwise positive? It never occurred to me. See? So anyway, so it's pointwise positive, and so we can remove the absolute value sign. That's very convenient because then this thing here just means that this function u, I mean, if I call this whole bunch u solves this differential equation. Okay? So yes, why did I do all this stuff? Of course, when we have the expert sitting here, I need to know how it works for the Schrödinger equation to then see if I can adapt this to the Dirac equation. Okay, and this does not look too hopeful. Let me skip this. This is just showing that it works. Because this is now the Hamiltonian. Suppose this is graphene, right? This is graphene with some landscape. I mean, this is a real landscape. Real landscape. This is some graphene with ripples. And I want to solve the eigenvalues of this Hamiltonian. So this is the Hamiltonian of graphene, right? So it's first order in P. It's not second order. It's first order. It's on the off diagonal. It's a 2x2 matrix. Give me the eigenvalues. Okay, it's not an elliptic operator. There's no maximum principle. It looks kind of hopeless. It looks hopeless. It doesn't work. So that's not good. So you can try obvious things. You can say, let's at least make it positive definite. It's not even positive definite, right? But we can make it positive definite by just squaring it, right? So you can square it, then it's positive definite. But the inverse is not pointwise positive. I mean, that's some magic of these elliptic operators, right? So it doesn't work. The inverse is not positive. So the first obvious trick fails. And in fact, I was not able to make any progress along these lines. I don't know how to do that. So I said, okay, I'm on ground zero. I have to start over again. And I started reading about positive matrices, non-negative matrices. And I found this book. And this solved it. This has a theorem which I didn't know about, Ostrovsky's theorem, which does it. And I think this is the first time, someone will correct me, this is the first time not only Ostrovsky's theorem, which is this thing which is called the comparison matrix, appears in physics. I'm betting on that this is the first appearance of the comparison matrix in physics. So what is the comparison matrix? Well, it exists, it has a Wikipedia entry. Comparison matrix means this. You give me a matrix, and then I do the following recipe, a bit of a crazy recipe, but I do the following recipe. I take absolute value of all the matrix elements, and then if they're not on the diagonal, I change the sign. That is the comparison matrix. So this is the recipe, right? So the absolute value, diagonal stays the same, and then off diagonal it's back. Sometimes it has to restart the Newton's equation integrator, and then at some moment it catches up, and it's back. Good. So mathematicians, of course, know about this thing. They have their own notation for it, which I could not use as a physicist, so I had to invent my own notation. The mathematicians call the comparison matrix, so matrix H, they call the comparison matrix this. They use these curly brackets, which of course for us is a no-go. These are bras and cats. It will confuse people to no end. So I needed a new notation, and I somehow introduced this notation. It's not a LaTeX primitive. If you write to me, I will send you the brief LaTeX code to make this object. So this is my notation for comparison matrix. And now comes Ostrovsky's theorem. And this is it, friends. Ostrovsky's theorem says the absolute value of the inverse of this operator, because remember, that's what I have in this inequality, right? I want to get rid of the absolute value sign. Before, I could get rid of them because this matrix itself was pointwise positive. But now, I can bound it by I can bound it by the inverse of the comparison matrix, and the comparison matrix is pointwise positive if it is positive definite. And that is the extra thing we need. So we need one extra thing, because this is not obvious. With the Green's function, of course, it was obvious that it was positive definite. Here, it's an extra piece. You do this construction here. A necessary but not sufficient condition for positive definites is that the diagonal elements are bigger than the sum of the off-diagonal elements. So if it dominates the off-diagonal elements in absolute value, the sum of them, then you're done. But it's not. That's a necessary. It's not. I mean, it's a sufficient condition. It's not a necessary condition. Anyway, this is it. This is Ostrovsky's theorem. And now we're done. Now we just plug this thing here, and now it just means. And notice, for the Schrödinger equation is its own comparison matrix, right? The Schrödinger equation, Laplacian plus v. Of course, the v is on the diagonal. The v was positive by construction. And Laplacian, you probably know how to discretize the Laplacian, right? To discretize the Laplacian, you put a 4 on the diagonal and minus 2 on the leading off diagonal. Right? That's how you discretize the second derivative. 4 on the diagonal, minus 2 on the off diagonal. So the Schrödinger equation is its own comparison matrix. That's of course why that's somehow you could say a special case of this thing. But this works more generally, and now, of course, there's the question is, yes, you get an inequality, but the inequality might be very bad. Might be some miserable landscape function up there, featureless landscape function, which doesn't tell you anything. So there, we just have to try. I have no math intuition there. Let's see if it works. So I do my favorite things. First, graphene, 1D Dirac Hamiltonian. Graphene discretized on the lattice will have a finite bandwidth. Of course, you might say graphene has an infinite bandwidth. It's a cone, right? The spectrum of graphene looks like this, right? This is energy versus K. But once you put it on a lattice, of course, it gets a finite bandwidth, so you can be close to the bottom of the band. And you could open a gap here. Bam, you could open a gap. So these would be two regions where you could investigate this, which I did. So this is near the bottom of the band, and this is near a band gap. This just shows, so I have both. Remember, this was the Hamiltonian. I had the Hamiltonian here, right? So I just to be very general, I have disorder in the potential, I have disorder in the mass. In graphene, this object here comes from a random substrate. It's graphene is carbon monolayer. It's on some random substrate, and that's why it has this random mass. We call it a mass, but it's a random substrate potential. This is just electrostatic potential. Put disorder everywhere. Hop, hop, hop. And so this is how it looks, right? Red and black are these disordered, total miserable, nothing to see. And you see here, so the blue peaks are the eigenfunctions, the localized eigenfunctions, and the red peaks is this landscape function. And it agrees pretty well, right? And it even follows the rule, the Villars-Mayburda rule, where highest peak is lowest eigenstate, and next highest peak is next lowest eigenstate. It really follows it quite religiously. So these are the energies. You see, these are the first energy and the second energy, blah, 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 blah. And so this is E1, that's the highest peak. This is E2, that's the next highest peak. There's an E3 here, and it really orders quite well. You can also see it kind of here. So this whole rule works well. I don't think I have anything like the n+1/4 magic eigenvalue rule. That would be too good to hope for that. No, I was not courageous enough to do that. I was not really. Yes, I was not courageous enough. I do say Michał Pachowski, who's really my very strong student who worked on this. He did spend, waste. You could say spend or waste. Perhaps even up to a year to try to do all the things you did, like Achmon distances, to really do much more sophisticated stuff rather than just this thing. None of it worked. So, excuse me? Okay, so my student was very smart, but it was not Terence Tao, so that's a good point. And anyway, so this is all I have. I don't have much more than that. But from my perspective, this is good enough. I knowing where the eigenfunctions localize is helpful. If you're in graphene, it's disordered. You could have all kinds of reasons why wanting to do that, including this is something, of course, which was also behind the whole program. Perhaps you can reverse engineer this and create potentials with localized special states. Anyway, this works. Now let's do somewhat which is a bit more, different flavor. That's a superconductor, a chiral P-wave superconductor. I mentioned this Hamiltonian also on Monday, right? So now we still have Px sigma x plus Py sigma y. That's always there, but now we have a P squared and we have a potential, but this is multiplied by sigma z. That's the crazy thing, of course, with superconductors. This is not spin up, spin down. This is particle hole, and so the potential is positive for an electron and negative for a hole. So this is it's called this Hamiltonian. The jargon in the field this is called a chiral P-wave superconductor. I could mention, just as an aside, this is one of the holy grails of condensed matter physics, to actually create a chiral P-wave superconductor in the lab. So unlike graphene, which also took us many, many decades to make it and was a Nobel Prize, I'm pretty sure the person who makes a chiral P-wave superconductor in the lab will win a Nobel Prize. But we don't have a reliable. So this material is purely a theorist thing, but there's hundreds and thousands of theory papers written on this thing because it's such a nice fundamental Hamiltonian. And same story here. So the way I plotted here is these spikes are the wave functions, the localized wave functions, and then the color is the landscape function. So if the landscape function works, these spikes should have a red peak, which they do, right? They're all red here on the top. So that somehow works also nicely, and good. So this is always near band bottom, right? I mean, I even either do it near band bottom, I could do it near band top, that's the same thing, or I could do it near a gap, but nothing else for that moment. I'm doing pretty well on time. Yes, please. Yes, I will. In fact, this is the next slide. Very good question. Next slide. Are there any other questions? It's a good question. I'm going to address this in just a moment. Are there other questions? No? Okay. Next slide. So I want to do something which is a little bit different than all of this. So I defined the notion of equimodular Hamiltonians. These are Hamiltonians which have the same comparison matrix. And so you would hope that Hamiltonians which have the same comparison matrix localize at the same point. Well, you say no, no, no. The answer is yes, yes, yes. I mean, at least I wouldn't tell you if it didn't work. So to do something a bit non-trivial, I used this paper here, which just appeared as we were wrapping up this research. It's actually a colleague of Svetlana Borshlovsky, who looked at Anderson localization in a complex potential. Right, so Hamiltonian is this minus Laplacian squared plus B1 plus IV2. And V is random. And there's some literature there which says that you can generalize Anderson localization to complex potentials. And they investigated this. They did it in 3 dimensions. I'm not courageous enough. I do it in 2 dimensions. So my premise would be that if I calculate the comparison matrix for this Hamiltonian, I get another Hamiltonian, which of course by construction will be Hermitian, right? Because the non-Hermitian part here is on the diagonal. I'm going to take the absolute value of this, and so I will convert this into a Hermitian operator. So obviously there will be no relationship between the eigenvalues. The eigenvalues of the Hermitian operator will be on the real line. These eigenvalues are somewhere in the complex plane. But I'm hoping that that the wave function will be at the same position because they have the same landscape function, right? And so 2 Hamiltonians have the same landscape function. So I would imagine that they localize at the same positions. So this is then the comparison Hamiltonian, if you wish, comparison matrix. It's a Laplacian, then it has an effective. Now you might be very naive and say, I'm just going to take the absolute value of this, but you shouldn't do that because the Laplacian itself will give you something on the diagonal. If you discretize the Laplacian, you get -4, or actually get bandwidth on the diagonal. So you have to somehow correct for that. Add the bandwidth, take the absolute value, and then subtract the bandwidth. This is the recipe. I mean, this is just a no-brainer. You just think about it, and then this is the result. So, yeah, we'll have to do a bit of work here. So, because the eigenvalues are, of course, very different. These are the eigenvalues of this comparison matrix. These are the eigenvalues of this Hamiltonian. I'm not even. Okay, it's a bit cheating, of course, you might say. Here I can order them. I can say, the ones which are smaller, so that's 1, 2, 3, 4, 5. Here's some I have to hunt for them. I would have loved to be able to somehow move through this diagram from left to right and say it's only the real part. It doesn't quite work that way. So it's 1, 2, 3, 4, 5. It somehow works. And this is then these are the plots, right? So these are the eigenvalues of H, and these are the eigenvalues of H effective. And so they lie on the same position. They're pretty well. So this is actually kind of neat. I'm not saying that this is very useful or fundamental, but it's kind of a new way to have a class of Hamiltonians which have the same location of eigenvalues, even though they're of eigenvectors, even though their eigenvalues are very different, because they have the same comparison matrix, the same landscape function. Now, the first slide said. The Rakamai-Rana fermions, right? That's what it said. So what about the Majorana fermions? Okay, Majorana fermions, that's the same Hamiltonian we had before. Here it is. I could add a p squared over 2m is a regularizer. It's important when you do numerics, but just to simplify stuff, I'm leaving it out. So I just have this Hamiltonian here. V is some random function. And this Hamiltonian, we discussed this on Monday, has particle hole symmetry. So there are states at 0. 0 is kind of the states of positive energy. They're matched by states of negative energy. And states at 0 energy, they're kind of like special. They're their own particle hole conjugate pair, and we call them Majorana zero modes. That's the jargon of the field. So Majorana zero modes are bound states of this, localized states of this Hamiltonian at exactly zero energy. And they're somehow stable, because if you have a localized zero mode at zero energy here, it cannot go up, it cannot go down, right? Because it would break particle hole symmetry. So E is zero is a stable point here. It's fixed here. And of course there is this obsession with Majorana zero modes, because then we braid them, we build a quantum computer. So I could imagine if you're working in that technology, you say, I need a landscape function to tell me where my qubits are. Doesn't it seem useful? You know, all this business, you say, why would I want to know where the state localizes? Well, here I tell you, in a quantum computer, the landscape function tells you where are the qubits. You have a disordered quantum computer, because it's based on this material. Where are the qubits? I don't know. But the landscape function, that tells us, so we know where to hook up the wire or how to start braiding them. So there's lots of, you know, typically if you write a paper, you know, you have to motivate it. If you send it to Nature or Science, what is the last sentence of any abstract of paper sent to Nature and Science? There's a idiom, a jargon term which is used in any paper sent to Nature and Science. Yeah, you know it! You know it! No, isn't this crazy? I'm an old man, right? At some moment, the word paved the way started to appear. It's a bit of an unusual English word, right? It's a high-level English word, pave the way. At one moment, it started to appear, and from that moment onwards, every single submission to Nature and Science paves the way. Of course, it's a very safe term, right? Because pave the way can mean anything, right? I mean, it's not that you reach it or you're there or whatever. This paves the way to low power consumption electronics, or beyond Moore's law electronics, who knows what. Yes, pave the way. Good. So yes, if we can do this, this is really cool. This has lots of potential. So I know how to find my fake landscape function. I have a fake landscape function. Fake landscape function is this: is you take the resolvent, give it a very small imaginary part. These are 2 by 2 matrices, right? So I take the trace, but trace just means of this 2 by 2 matrix degree of freedom. So it still has the coordinate variables. I take the diagonal elements, and this is my inequality. Psi x squared is smaller than I epsilon trace resolvent. And it works brilliantly, right? So here you see this is just a plot. The contours are the localized states, and the colors are the landscape function and landscape function, this particular function here, and it works very well. Now you might say, why? Okay, then we're done, right? Well, here I need to calculate the resolvent. I need to invert the matrix. So that's somehow cheating, right? The whole idea of landscape function was solve a PDE. In fact, if you tell any condensed matter physicist, I can find localized states by calculating the resolvent, they'll tell you, yes, of course, we call this the local density of states, right? So this is yeah, it looks neat. And actually, you could even argue that it's computationally kind of effective. Why not? I mean, you have to invert the matrix, but you only want to have low-lying eigenstates. As you can understand, I cannot write a paper and send it to any journal and say, I've discovered a new landscape function. And then some referee will say, sir, you've rediscovered the local density of states, right? So that's dangerous. So this works like a charm. But yeah, Jens Barderson, he was actually my student. He managed to pull this off. He managed to send a paper to a journal and sell the local density of states as a landscape function. But okay, I'm not courageous enough for that. So this is it. Now, people who work in my group know that occasionally I'll have problems which I've worked on for a long time, and I'll be very, very frustrated. And then I offer bottles of one bottle of champagne for someone who solves it. Of course, with not just the bottle, but also with the honor and the esteem which comes with that. So here it is, friends. If anyone can find a landscape function for this Hamiltonian, landscape function, so don't come to me with this guy. Just anything which, like, say, solve a PDE, that kind of stuff, right? And which somehow then allows me to do something which is of similar quality of here. Then here it is. It's waiting. Bottle. I'll send it. No, I give it now. This is what I do with my group. I do this with my group, but now you're here, and now I give it to you. I do it because, I do it with some assurance that I will not have to pay up, because we really tried. No, I guess we tried for a full year. All kinds of variations, all kinds of stuff. We tried everything under the sun, and we couldn't find anything. We only found stuff which works near the bottom of the band. You know, it's a bit of an unusual problem. Typically, you think about localization, you say, let's go to low energies, let's go to high energies, let's go near a band gap. And the Majoranas don't live there, right? They don't live at low energies, they don't live at high energies. They live right at E0. That's the physics of this problem, right? So it's a very unusual situation. I cannot solve it near band center. Oh my goodness, no, it's just, I don't know, it's just that. Now, of course, Svetlana will immediately correct me and say, no, it's not like that. But in my experience, the landscape function is very efficient to tell you what happens near band bottom. It just have a big band, right, a cosine band. And it's very efficient to tell me what happens near the bottom, but it's not efficient to tell me what happens near the center of the band. Just doesn't, it's not informative, at least not informative to tell me where it localizes. Perhaps you can do other things, and we've seen other things, right? Mobility threshold, we've seen other things. But just this simple thing here, do I have something which tells me, in fact, this was also the conclusion of Barderson, right? The conclusion of Barderson was also, if you want to do Anderson localization near band center, this was just Schrödinger equation. If you want to do Anderson localization near band center, you need to work with the local density of states. And yes, we know that, and it's not particularly helpful. So no, this is just so. I think I formulated the problem in a pretty precise way here. So give me a plot which looks like this, where the landscape function requires me to solve a PDE. And then there will be eternal fame, and yes, lots of other stuff. We're done, friends. Thank you for your attention.